Hello! Today, we're going to solve a fascinating problem in mathematics, specifically in the area of functional equations. Our goal is to find all functions f that map real numbers to real numbers, such that for any real numbers x and y, the equation f of the quantity x times f of x plus f of y equals f of x squared plus y. This might seem intimidating at first glance, but the strategy for solving these types of problems often involves a process of substitution. We'll pick specific values for x and y to simplify the equation and extract useful information. By the end of this video, you will be able to solve this functional equation. Let's begin by making our first substitution. We want to choose values for x and y that can simplify this complex equation. A great starting point is to see what happens when the term inside the function on the left side, x times f of x, is equal to 0. If f of x is 0, for some value of x, it will eliminate that whole term. So, let's explore if there exists a number, we'll call it c, such that f of c is equal to 0. This is a common and powerful technique in functional equations. If such a k exists, we can substitute it into our original equation for x. We'll replace x with c, and remember that we are assuming f of c is 0. The equation becomes f of the quantity c times f of c plus f of y equals f of c squared plus y. Now, we can use our assumption that f of c is 0. Watch how everything simplifies. Since f of c is 0, the term c times f of c becomes 0, and the term f of c squared also becomes 0. This leaves us with a much simpler equation, f of y equals y. Let me repeat that, f of y equals y. This is a massive discovery. This equation, f of y equals y for all real numbers y, tells us that our function f must be an involution. That is, applying the function twice returns the original input. For example, if f of 3 is 7, then f of 7 must be 3. However, this result hinges on the existence of the special value c, where f of c is 0. Our next step is to prove that such a c must exist. So, we've shown that if f of c is 0, for some c, then the function f of y equals y. Now, let's turn this logic around and prove that a value c where f of c equals 0 must exist. In other words, we need to show that 0 is in the range of f. To prove something, it's often useful to assume the opposite is true and see if we can reach a contradiction. This is a technique called proof by contradiction. Let's assume, for the sake of argument, that f of x is never 0 for any real number x. In this case, f has no root. If f of x is never 0, then the term f of x squared is always a positive number for any non-zero value of x. Let's substitute x equals sign 0 into our original functional equation. We get f of y equals f of 0 squared plus y. Remember, we are still operating under the assumption that fx is never 0, so f of 0 is certainly not 0. This means f of 0 squared is a positive constant. Let's call this positive constant a. So we have f of y equals a plus y. This equation tells us something powerful about the range of f. Because a plus y can take on any real value by choosing an appropriate y, it means that the set of values that f of y can be is the entire set of real numbers. In other words, the range of the composite function f of f is all of R. This implies that the range of the original function f must also be all of R. This is a property of functions and their ranges. So, our assumption that f has no roots led us to the conclusion that f takes on every real value. But if f takes on every real value, it must take on the value 0 at some point. This is the very definition of a root. This creates a direct contradiction with our initial assumption. Our assumption must be false. Therefore, our initial assumption was false. There must exist a real number c such that f of c is equal to 0. This confirms our key result. Now that we've definitively proven that a root c exists, we can fully rely on our first major finding. We know for certain that there exists a c such that f of c is 0. And, as we showed, this leads directly to the conclusion that f of y equals y for all real numbers y. This property is incredibly valuable. It means the function f is a bijection and is its own inverse, Knowing this allows us to explore a second substitution. Let's substitute y equals c into the original equation. This is a strategic choice because we know f of c is 0, which will simplify parts of the equation. Plugging in f of c equals 0, we get f of the quantity x times f of x equals f of x squared plus c. This is another key relationship between f of x and x. We now have two critical pieces of information. First, f of y equals y. Second, f of x times f of x equals f of x squared plus c. Let's see if we can use the first to simplify the second. Our goal is to understand the structure of the function f. Let's start with our result f of x times f of x equals f of x squared plus c. How can we introduce the f of f property? Well, let's apply the function f to both sides of this equation. Applying f to both sides gives us f of the quantity x times f of x equals f of the quantity f of x squared plus c. On the left side, we have f of some expression. We know f of anything is just that anything, so the left side simplifies dramatically. The left side simplifies to x times f of x. The right side remains as f of the quantity f of x squared plus c. This new equation connects x times f of x to f of x squared plus c. This is a powerful identity that we will explore in the next scene. Let's summarize where we are. We have proven two key facts. The first is that f of x equals x for all real numbers x. The second is the identity we just derived. X times f of x equals f of the quantity f of x squared plus c. So, our next logical step is to substitute this identity back into our first equation. F of x equals x. This might seem like a bit of an algebraic dance, but it will help us eliminate some complexity. Our goal is to isolate f of x and find its form. The original equation is f of x equals x. Let's think about this. It means that if we know the input is f of x, the output is x. Our new identity says the input x times f of x gives the output f of x squared plus c. Let's apply f to our identity. This gives us f of x times f of x equals f of the quantity f of x squared plus c. Now, we can simplify the right side using the f of f property. Remember, f of anything is just that anything. So the right side simplifies to just f of x squared plus c. This gives us the equation f of x times f of x equals f of x squared plus c. This looks familiar. It's the exact same equation we found by substituting y equals c into the original equation. Let me point that out again. This means we haven't created a new independent result. This indicates that we should probably consider the term f of x squared plus c as an input to our function f. To proceed, we need to analyze two cases based on the value of c. Our analysis has led us to the relationship f of x times f of x equals f of x squared plus c. Now we must consider the two possible cases for the value of c. The constant c came from our substitution y equals c, where c is a root of the function f. We need to explore if c can be 0 or not. Let's first tackle case 1. C equals 0. If c is 0, the root of f is at x equals 0. This means f of 0 equals 0. If we substitute c equals 0 into our equation, we get f of x times f of x equals f of x squared. This must hold for all real numbers x. Let's use our f of x equals x property. Applying f to both sides gives f of x times f of x equals f of x squared. This simplifies to x times f of x equals x squared. So, we have f of x squared equals x times f of x. Let's look at this carefully. It seems to imply something specific about f of x. We found two important results. Let's substitute x times f of x equals f of x squared back into our main equation for c equals sign 0. The original equation is f of x times f of x plus f of y equals f of x squared plus y. Let's apply f to both sides of the full original equation, remembering that f of z is z. The left side simplifies to just x times f of x plus f of y. On the right side, we use our results to simplify. F of x squared is x squared, and f of y is f of y. We're almost there. In the next scene, we will use this equation to pin down the exact form of f of x for the case c equals 0. We are still in case 1, where c equals 0. We've derived a new identity, x times f of x plus f of y equals f of the quantity f of x squared plus y. Let's work with this identity. The first step is to use the property we found earlier for c equals 0. which states that f of x squared equals x times f of x. Substituting this in, we get x times f of x plus f of y equals f of the quantity x times f of x plus y. This is a very important form. It tells us that f of the sum of two terms is the sum of the f values of those two terms. This looks a lot like a Cauchy functional equation. The left side is the sum of f of the x part and f of the y part. The right side is f of their sum. This property must hold for all x and y. Let's check this again with a different manipulation. We know f of x times f of x equals f of x squared. Applying f to both sides gives x times f of x equals f of x squared. Now let's go back to our identity x times f of x plus f of y equals f of x times f of x plus y. Let z equal x times f of x. If we let z equal x times f of x, and we use our previous finding that this is equal to f of x squared, we get f of the quantity f of x squared plus y equals x times f of x plus f of y. This confirms a property called additive linearity. The function f must be linear. We know f of 0 is 0, so the linear function must pass through the origin. Therefore, f of x must be of the form f of x equals kx for some constant k. We've established that the function f must be a linear function passing through the origin, so f of x equals kx for some real number k. In the next scene, we will substitute this candidate solution back into the original equation to find the value of k. We're almost at the finish line for case 1. We have determined that if c equals 0, the function must be of the form f of x equals kx. Now we need to find the value of the constant k. To do this, we'll substitute our candidate solution, f of x equals kx, back into the original functional equation and solve for k. The original equation is f of x times f of x plus f of y equals f of x squared plus y. Let's perform the substitution step by step. First, let's substitute f of x equals kx and f of y equals ky into the left side of the equation. The left side becomes f of the quantity x times kx plus ky. Now, because we assumed f of x equals kx, we can apply the function f to the expression inside. So the left side simplifies to k times the quantity kx squared plus ky, which is k squared x squared plus k squared y. Now let's do the same for the right side of the original equation. The right side is f of x squared plus y. Substituting f of x equals kx, we get kx in parentheses squared plus y. Now we set the simplified left side equal to the simplified right side. We have k2x squared plus k2y equals k2x squared plus y. We can subtract k squared x squared from both sides, which simplifies the equation considerably. This leaves us with k squared y equals y. This equation must hold for all real numbers y. The only way k squared y can equal y for all possible values of y is if k squared equals 1. This gives us k squared equals 1. Taking the square root, we find two possible values for k, 1 and minus 1. Remember, this is the solution for the case where c equals 0, meaning f of 0 is 0. We have found two potential solutions for case 1, where c equals 0. Let's verify them, and then move on to case 2. The two solutions for this case are f of x equals x and f of x equals negative x. Let's check the first solution, f of x equals x. We substitute this into our original equation. We get f of the quantity x squared plus y equals x squared plus y. And indeed, because f of x equals x, f of anything is just that thing. So, f of x squared plus y is x squared plus y. The left and right sides are equal. So f of x equals x is a valid solution. Now, let's check the second solution, f of x equals negative x. Again, we substitute this into the original equation. We get f of the quantity negative x squared minus y equals x squared plus y. Because f of x equals negative x, f of the left side is the negative of the left side. So the left side becomes negative of the quantity negative x squared minus y, which simplifies to x squared plus y. This is exactly what's on the right side, so f of x equals negative x is also a valid solution. We have successfully found two solutions. Now we need to determine if there are any others from case 2, where c is not 0. Remember, the constant c was defined such that f of c is 0. Our next task is to explore if c can be a non-zero number, which corresponds to the case 2. Let's begin exploring case 2. Our assumption here is that the root of the function c is not equal to 0. Remember, for this case the equation f of y equals y still holds. We found this result by proving that a root c must exist regardless of its value. So f is still its own inverse, which is a powerful tool for manipulation. Our key relationship was f of x times f of x equals f of x squared plus c. Let's start with this. This equation tells us that applying f to the term x times f of x gives us the value f of x squared plus c. Now, let's consider the value of f of x for x equals c. We know that f of c is 0. Substituting x equals c into the equation gives us f of c times f of c equals f of c squared plus c. Now we use our condition for this case. F of c equals 0. Substituting 0 for f of c, the left side becomes f of 0, and the right side becomes 0 squared plus c. This simplifies to f of 0 equals c. This is a very important relationship. The root of the function is c, and the value of the function at 0 is also c. Let's summarize this finding. In case 2, where c is not 0, we have f of c equals 0 and f of 0 equals c. These two facts describe a symbiotic relationship for the function f. Knowing this, let's substitute y equals 0 into the original functional equation. Since f of 0 equals c, the equation becomes f of the quantity x times f of x plus c equals f of x squared. Let me restate that. So, we have f of x times f of x equals f of the quantity x times f of x plus c. Now, if we compare this to our previous key result from the beginning of case 2, f of x times f of x equals f of x squared plus c, you'll see a contradiction. Let's look closely at these two equations. They are identical except for the term inside the function on the left side. The first equation tells us that applying f to the term x times f of x plus c results in f of x squared. The second equation tells us that applying f to the term x times f of x results in f of x squared plus c. Let's think about this. If c is not 0, then the inputs x times f of x plus c and x times f of x must be different. Yet, when we apply the function f to these two different inputs, their outputs are also different but in a specific way. One output is exactly c greater than the other. This is the source of our contradiction, which we will formalize in the next scene. Let's formalize the contradiction we found in case 2. We are in the case where the root c is not 0. We derived two equations, the first from setting y equals c and the second from setting y equals 0. From the first equation we can write f of x squared as f of x times f of x minus c. Let's substitute this into the second equation. Substituting this expression for f of x squared gives us f of the quantity x times f of x plus c equals f of x times f of x minus c. Let's define a new variable to simplify this. Let's say z equals x times f of x. With this substitution, our equation becomes f of z plus c equals f of z minus c. This must hold for all values of z that can be expressed as x times f of x. Is this a valid relationship? We need to determine the range of the expression z equals x times f of x. We know that the range of f is all of R. This implies that the term x times f of x can take on any real value. Therefore, this relationship, f of z plus c equals f of z minus c, must hold for all real numbers z. This equation states that f is not just an involution, but specifically an affine function with a particular slope. The difference in the function's output is exactly the negative of the difference in its input, when the input difference is c. Now we can use this property along with the fact that f is an involution, f of z equals z. Let's apply f to both sides of our new equation. We get f of z plus c equals f of the quantity f of z minus c. Using f of z equals z, the left side simplifies to z plus c. This gives us z plus c equals f of the quantity f of z minus c. This equation must hold for all real numbers z. Now, let's substitute f of z equals z into this equation. If we substitute f of z equals z, we get z plus c equals f of the quantity z minus c. But from our relationship, f of z plus c equals f of z minus c. If we swap z with z minus c, we get f of z equals f of z minus c, which means f of z minus c equals f of z plus c. So we have a contradiction. On one hand, f of z minus c is z plus c, On the other hand, f of z minus c is f of z plus c. Substituting z minus c for z in our first derived equation gives f of z equals f of z minus c. This is a direct contradiction. The assumption that c is not zero leads to a logically impossible conclusion. Therefore, our assumption must be false. The root c cannot be non-zero. It must be that c equals 0. This proves that case 2 has no solutions. Let's bring it all together. Our investigation of the functional equation began by exploring the properties of its root, c, if one exists. We proved that a root, c, must exist. This led us to the powerful conclusion that the function must be an involution, meaning f of x equals x. We then branched into two cases based on the value of this root. The first case was when c equals 0, meaning f of 0 is 0. For this case, we showed that the function had to be linear and pass through the origin. By substituting the form f of x equals kx into the original equation, we found two solutions, f of x equals x and f of x equals negative x. We verified that both of these are valid solutions. The second case was more involved. We assumed that c was not 0. In this case, we found a contradiction by substituting y equals c and y equals 0 into the original equation. The assumption that the root c is not 0 led to a logical impossibility. Therefore, there are no solutions in this case. So, combining our findings, we have arrived at the complete set of solutions. The only functions that satisfy the given equation are f of x equals x and f of x equals negative x. These are the two functions that fulfill all the conditions. You can now confidently solve this functional equation.